Hello student, today we are going to solve one numerical example based on a power method, means how we find a numerically largest eigenvalue with the help of a power method. So, here already we write the problem is find the numerically largest eigenvalue and corresponding eigenvector of a matrix A. So, as we know that how we find the numerically largest eigenvalue using the power methods, here we write using the power method, using the power method, using the power method, using the power method. So, as we discussed in a previous lecture, first of all we consider one eigenvector arbitrary, which is not orthogonal to x1. So, here we consider x1, here let x1 equal 1 0 0 1 0 0 with the approximate eigenvector corresponding to the numerically largest eigenvalue, numerically largest eigenvalue. Now, then we pre-multiply by the matrix A. So, pre-multiply by the matrix A. So, what will happen here? Ax1 equal pre-multiplying by matrix A in x1, then ax1 become here we write ax1, the value of A is 25 1 2, first row with 25 1 2, second row with 1 3 0 1 3 0, third row with 2 0 minus 4 2 0 minus 4 multiplied by the approximate eigenvector 1 0 0. The value of this after multiplication, the value become 25 1 2, 25 1 2. In order to normalize the numerically largest value of this eigenvector, in order to avoid the round off error, here we take outside 25 and divided the all the element by the 25. Then first element 25 by 25, this become 1 by 25, this become 0.04, and 2 by 25, so this becomes 0.08. So, what is the value? This equal 25 into 1 0.08 0.04, 0.08, and for the next iteration we assume that this is a approximate vector. So here we write 25 x2, 25 x2. Again pre-multiply by matrix A, because what is the procedure in a power method? In a power method, first of all we approximate one eigenvector corresponding to the largest eigenvalues, then be pre-multiplied by the matrix A, and in order to avoid the round off error we divide all the element of a eigenvector by the numerically largest value. So here numerically largest value with the 25. So to convert the largest element equal to 1, in order to, in our normalization we convert the numerically largest value equal to 1. So here we divide by the 25 and take outside. So this 25 be the approximate eigenvalue, and this was a approximate eigenvector for the next iteration. So in the next iteration again we pre-multiply by the matrix A. So this is considered as a x2, this one is a x2. So now ax2 become, A is again 25, 1, 2, 1, 3, 0, 2, 0, minus 4, multiplied by 1, 0.04 and 0.08. 0.08. So now this one equal to what? This one equal to first row by the first column. So this row, first row by this column, then 25 plus 0.04 plus 0.16. This is a element of a first element. Similarly, second element will be multiplied by second row by this column, then 1 plus 0.12, and third row by this column 2 plus 0 minus 0.48 is 32, 0.32. So if we simplify this expression, then this expression become 25.2, 16 plus 4, 0.20, 25.2, 1.12 and 2.2 minus 3.2, 1.68. So already we write here this become 25.2. So if we write after this, then ax2 become what? ax2 become 25.20 and second become 1.12, 1.12 and third become 1.68. So again, in order to find out the next approximate eigenvector, we normalize the numerically largest element. So how we normalize the numerically largest element? Here numerically largest element is a 25.2. So we divide all the elements by 25.2. So in order to normalize the eigenvector, AX2 become 25.2 into this become 1.12 divided by 25.2, and third element become 1.68 divided by 25.2. So now we simplify these expression, then we find what? We find the eigenvector, approximate eigenvector corresponding to the largest eigenvalue. Now largest eigenvalue up to this iteration is a 25.2, and eigenvector be the 1.12 divided by 25.2, 1.68 divided by 25.2. So we repeat this process until we get in a successive iteration the approximate eigenvector become equal. So we repeat this process, already we calculated, and right here after division of this 1.12 divided by 25.2, 1.68 divided by 25.2, this is the result. AX2 equal after simplification of this expression 25.2, 0.0440, 0.0667. So for the next iteration, this is the third approximate, means eigenvector corresponding to the numerically largest eigenvalue. So here we write a 25.2 into x3, and we repeat this process. So as you see here, already we write, means again we pre-multiplied by a, then this is the result 25.1778, 1.1332, 1.7337. So in order to normalize the numerically largest element, which one is a numerically largest element? Among these three, 25.1778 is a numerically largest element. So we take outside. In other words, you may also say we divide all the element by 25.1778. So the numerically largest element converted into a 1. Then after dividing this 1.1332 by 25.1778, we get a 0.0450. Similarly, 1.7337, 0.0688. So for the next iteration, this vector x4, this vector is treated as a approximate eigenvector for the next iteration. Similarly, again we pre-multiplied by a in a vector x4, then we get this eigenvector x5, and again if we multiply, then we get 25.1821 into x6. So if we closely observe the x5 and x6, x5, what is the value of x5? x5 become 1 0.451, 0.451, 0.685, 0.685, and also x6 become 1 0.451, 0.685. Now x5 and x6 both have a same values. So we stop our iterative process here, because now in a 2 successive iteration we able to find out the same eigenvector. So this is our approximate eigenvector corresponding to the numerically largest eigenvalue. Thus, since x5 equal to x6, thus eigenvector thus 1, 0.451, 0.685 is the eigenvector corresponding to numerically largest eigenvalue. Where is the numerically largest eigenvalue? The factor, this factor is a numerically largest eigenvalue. This factor is a numerically largest eigenvalue, because we able to find out ax5 equal lambda x6. Here 25.182. So this one is a eigenvalue, largest eigenvalue. Why this one is a largest eigenvalue? You may also say like this one. We know that x is a eigenvector if ax equal eigenvector corresponding to lambda if ax equal lambda x. Here what will happen? Here ax5 equal lambda x6 after the last iteration, ax5 equal lambda x6. Now since x5 equal x6, so you may write here ax5 equal lambda x5. Thus lambda is a eigenvalue corresponding to the eigenvector x5, because we able to find out x5 equal x6. So now this one is all about this problem. Be able to find out a largest eigenvalue and corresponding largest eigenvector.